we've been talking about reaction kinetics, and what our goal is right now is to try to determine whether or not a given mechanism, a proposed mechanism, is plausible. So this was our overall reaction, and there are 3 different possibilities. So as we look at this, Anne comes along and she says, you know what, I think this happens just as it is written, that it truly is a termolecular reaction. Now, what we have to do is do our 2 checks. Does it match with the stoichiometry? Well, yeah, this one matches because it is the stoichiometry. So this does agree with our balanced stoichiometry. So it passes that test, and I'm going to be honest with you, most of them will, but I want you to get into the habit of checking that. Now, the question is, does it match with the experimentally determined rate law expression? So experimentally, it was found to be first order with respect to nitrogen dioxide and first order with respect to fluorine. So our mechanism has to agree with what we see in the experiment. Now, to do that, remember we take our rate is going to be the proportionality constant. We call the rate law constant or the rate constant. And we always do this from the reaction side of the arrow. So I would put my concentration of NO2. Now, since this is an elementary step, by definition, that's what mechanisms are the elementary steps. I can use the stoichiometry. Can't use it if it's an overall, but I can this time. And then I would multiply it by F2, and that would be implied to the first. Well, that's out. That does not agree with the experimentally determined first order and first order. So, what we would say as scientists is, well, this is not going to help me move on to my next level of experimentation, so we're going to ignore that one. Now, the next 2 look very, very similar, but they have one key distinction, and that distinction is which they're defining as our slow step. So let's first take a look at how we add reactions together. A critical skill to wrap your minds around. We'll do this at least for the next 3 or 4 units. So you want to make sure you pay close attention to what I'm about to do. We are going to treat the arrow as if it's an equal sign. Mathematically, if you have the same number on both sides of the equal sign, and it's the same operation, which here it's all addition, we can cancel it. So when I add these 2 reactions, if there is a substance that shows up as both a product and a reactant, or honestly a reactant and a product, then we can cross it off. It cancels. In other words, there's no net involvement of that fluorine. I have a special name for it we're going to come to in just a minute. Now, once you've crossed off everything that's alike on both sides, you simply bring down what's left. So I have 2 NO2. I'm going to leave the states as they are. You can see those. And then I'd make 2 NO2F. So this meets our first criterion of matching the stoichiometry. And since our second reaction's identical, we can say this one also matches that stoichiometry. Now, here's where they really differ. And we'll do more of that adding of reactions, by the way. So kind of start getting your mind around that a little bit. Here's where they differ. This one says this is the slow step. Remember, your slow step is your rate determining. Remind me in class to show you a little video clip of an I Love Lucy episode at the chocolate factory. And we see how the conveyor belt was the rate determining step, but very, very quickly, Lucy becomes the rate determining step in this case. It's a very amusing little clip. Now, we're going to get then our rate law from our slow step, but it's got to be the slow elementary step. So we would say in this rate is equal to K. We always go again on the reactant side of that arrow, and it would be NO2 to the first, and then it would have F. Okay? Now, there's a problem with this one. F is not a catalyst. You'll see why soon, and you do know catalysts speed up a reaction. You know that much. It's not a catalyst, and it doesn't show up in our overall. So this cannot show up as part of our rate law expression. And so this is not plausible. It doesn't agree with our experimentally determined, and we're going to see this fluorine that formed and then disappeared can't show up. And so that's not good. So right now we've pretty much eliminated 2 mechanisms as being not worthy of further study. Now let's take a look at this last one. We're going to again go by the slow step. So the rate will equal our constant. We always go on the reactant side of an elementary step. And it'd be NO2 to the first. I'm being explicit here. I don't expect you to. I'm just trying to help you see that in an elementary reaction, we can use those stoichiometric coefficients. I don't expect you to put 1s there. Now, this meets our second criterion. Okay? It matches the stoichiometry and it matches the experimental rate law. And so what that tells us is that this mechanism here is the one that would be worthy of further investigation. Okay? So that's all it's saying. It's not saying it is the mechanism. It's saying it's plausible. So we as scientists are going to want to start looking for the presence of substances like this F that show up in the middle and go away. All right, so we'd want to find ways to identify and look more detail at the molecular level. Now, let's take a look at some of the terminology we've used as a way to tie it together. That substance that was formed and reused, monatomic fluorine in our last example was one of these, is called an intermediate. Intermediate's going to mean between, right? And I like to use the idea of a party. Now, let's talk about the catalyst. I'll come back to this transition state in a minute. You see that. I think it's a pretty self-evident definition, so I'm going to leave that to you. The key is that partially broken, partially formed, okay, concept. Now, a catalyst increases the rate, and it can do this in 2 ways. It can stabilize the transition state that we've talked about before, or we can form a new transition state. Either way, it is something that has a lower activation energy. That's key. And I want you to write that in there. Sometimes it's important to write things in. A lower activation energy by stabilizing or forming a new transition state. So we can think of the catalyst as kind of like your mom at the beginning of the party, and an intermediate's like a party crasher. So at the beginning of the party, your mom is helping you get ready for your party, but then mom's going to go away, right? She may check in on you every once in a while, but basically mom's going to go away. But then what is mom going to do? She's going to come back at the end. So at the end, mom will come back. She's there at the beginning to help you set up. She'll come back at the end to help you clean up and make sure everything's okay. All right. So if you want to think, another analogy I was trying to come up with is a sandwich. Mom would be the bread on either side. All right. It's not the best analogy, but it's something that kind of came to my mind. Now, an intermediate is kind of like the party crasher. Party crasher was not invited. It's not there at the beginning. The party crasher shows up in between. It's formed and then it's reused in the mechanism. It goes away. So this is not present at the beginning. This is only present at the middle parts, whereas a catalyst is there at the beginning and the end. I think you'll see it a little bit better if we do a quick reaction or a quick example of that. So let's take a look at this example here. Here's a suggested mechanism, and let's get the overall reaction and see what it's a suggested mechanism for. And we want to eliminate things that show up on both sides. So this showed up, notice it wasn't there at the beginning, showed up, and then it went away. Okay? Now, substances that show up, it crashed the party and then got kicked out, that's the intermediate. Okay? Now, a substance that is present at the beginning, like your mom, and then reforms at the end, beginning and end, is a catalyst. So IO minus is our intermediate, I minus is our catalyst. Our overall reaction is 2H2O2, one here, yields 2 waters plus an oxygen. Now, this might show a type of potential energy curve you'll see for a two-step mechanism. I just learned how to do this, reasonably well on Word. So this is your reactant. So the reactant reacts with possibly a catalyst, and it forms an intermediate. Now, this would be an activated complex up here. This is going to be a different activated complex. Now, then the intermediate is going to react and go on to form product in this two-step. Okay? And so our slow step, I hope it's logical that the slower step has the highest activation energy. That's what I was trying to depict in here, that it's more likely, if not always likely, that this is going to have the highest activation energy compared to the fast step. Okay? So that's going to take more energy to get over, so it's going to be slower, and then the intermediate takes less energy to go on to product, so it's a faster step. And the rate always is determined by the slowest step. Okay? So catalyst is there at the beginning, goes away, and it's there at the end. A catalyst shows up in the middle, and then it goes away. Okay? So that's how you're going to be identifying those. Okay? Now, I have another couple of good examples for you. Let me do one more, and then we'll do the fast equilibrium one. All right? So this one says give the reaction mechanism based on this proposed mechanism. We want the rate law expression. So we're going to write the rate law, and we're going to look for catalysts or intermediates. Okay? Now, the rate law we can get right away, because the rate law, if it's an elementary step, we can get it right from the slow step. So our rate law expression is going to be rate is equal to the rate constant times NO2 squared, because that's really 2 NO2, right? Another way to write that would be 2 NO2s. So that's 2 NO2 squares. So that would be the rate law expression we would obtain from this. Now let's identify substances that get canceled. All right? Now, NO2 is present in a reactant, and it shows up nowhere as a product. NO shows up, but then it stays. It doesn't, it's a product and a product. It has to be a product and a reactant, or a reactant and a product to cancel. So NO is just products. It doesn't cancel. NO3 is a product here, and it's a reactant here. So NO3 will cancel. And since it shows up in the middle and then goes away, it's consumed. That's what we would call our intermediate. So NO3, nitrogen trioxide, would be called an intermediate for this reaction. Okay? And I don't see a catalyst. If we wanted to go ahead and add this up, you just bring down what's remaining. I have 2 NO2s that aren't crossed off. Yield, I've got 1 two NOs that weren't crossed off, and I have an oxygen that wasn't crossed off. Okay? Now, these are a little tricky. You'll have plenty of time to work on them between WebAssign and AP. So if you don't understand this, I want you to put a star by it. And before we get started in class, don't let me forget to answer your questions, because sometimes I really get into the whole dynamics of getting the class started and I forget. And your questions are too important to forget. So make sure I answer your questions. Until then, this is signing off.